if you ever go to a major university, typically what happens is you have the faculty member teaching the class, and you have a bunch of graduate students that actually look after you. So I remember when I was doing my PhD, we had the freshman chemistry, there were 1,200 students in it, and I was in charge of 31 students. So, so that was a big, big class. So, and oftentimes they would run discussion sections, and this is kind of what it is. This is kind of what, like if you, except, you're getting a faculty member teaching instead of a graduate student. So depending on where you go, they call them at Manoa, if you go to Manoa, they call them TAs. At Berkeley, they call us GSIs, graduate student instructors. So it depends on, yeah, TA is probably more common than GSI. So, but I was reviewing your homework, and also just from the class, I saw a few weak spots, and I'm gonna kind of go over what I perceive to be the weak spots, and I have some other stuff prepared from chapter 1 and 2 if we need to, but I kind of focus on 3 and 4. Because in general speaking, chemistry is cumulative. I mean, so you need all the stuff from previous stuff that builds up on the next stuff. So it's just kind of cumulative by nature. So that's what we're doing today, problem session. And let's see here. So here is chapter 3, question 89. What's the empirical formula? And we're going to look at the empirical formula for nicotine. So nicotine is 74.03% carbon, 8.7% hydrogen, and 17.27% nitrogen. So with percents, you pick any number. So pick 100 grams. That's what I just do. I just pick 100 because that's a nice, easy number. And then you have 74.03 grams of carbon, 8.7 grams of hydrogen, and or nitrogen, 17.27 grams nitrogen. And so next thing you need to do is convert to moles. No. Oh. Convert to moles, mole carbon, 12.01 grams carbon. Where I'm getting this number from, I mean, I know I have it over here. I wrote that down for reference. But if you look at the periodic table, it's the numbers, you can even see it in the intro. It's the numbers on the bottom. So carbon here, and it's 12.011. I guess I'm just going down to the 100th place. Hydrogen, so mole hydrogen, 1.008 grams hydrogen. Again, the bottom number on the periodic table. And then mole nitrogen, 14.01 grams nitrogen. Everyone doing okay? How I'm getting so far? Where are these numbers coming from? Okay, so then doing this, you get 6.164 moles of carbon, 8.631 moles hydrogen, and 1.233 moles nitrogen. And what do you do next? You divide by the lowest number. The lowest number is 1.233. So you divide everything by 1.233, and you get 7 moles carbon I'm sorry, I was reading, it's 5 moles carbon to 7 moles hydrogen to 1 mole nitrogen. So, and you can stop there because there's no fractions. So meaning that nicotine is going to be C5H7N. I think it's double that. I remember checking, I was checking it, so I looked it up on Google. What's the formula for nicotine? Yeah, so the formula for nicotine actually is C10H14N2. This is the actual. So I mean, with the empirical formula, that's the lowest ratio. So I mean, like glucose is C6H12O, it's going to be CH2O for glucose, the empirical formula there. So from these data, we can infer that nicotine is 5 parts carbon to 7 parts hydrogen to 1 part nitrogen. But in actuality, the molecule is double that. So at this point in time, you don't have to know how to do this. I'm just using that as a check. You do know how to do that. So question, yeah.
How do you know which order to put the elements? Is it based on their percentages?
No. I guess in that regards, you don't have to worry about that too much this point in time, especially in a multiple choice test, because it'll give the order right there. As far as which one goes first, the biggest, least electronegative atom goes first, and you haven't learned what that means yet. So
That's not on the test.
yeah, not on the test. The metals go first. So other questions? So good question, not on the test. Well, that's important to know. All right, so balance these chemical equations. So I saw actually a lot of students are having issues with balancing chemical equations. I know when I do this, I usually don't include the states, but when you do the mastering chemistry, you need to do the states. So let me show you how to do this one. So I'm going to do 8 examples. So A here, CO2 plus calcium silicate plus water yields silicon dioxide plus calcium bicarbonate. Okay, so looking at these, it's important to identify ratios. So as I'm looking through this right now, I can see that for calcium, there's 1 calcium atom there, and I'm using a different color if you're colorblind. I'm marking silicon with a different color there. Well, although I must say, if you notice that calcium and silicon are in the second in this molecule there, and calcium and silicon are found in each of the other 2 molecules. So actually, I can fix the ratio of this molecule and this molecule and this molecule. So these ratios are not going to change. So for every one of the calcium silicates that I have on the left of the equation, I'm going to have 1 unit of silicon dioxide and 1 unit of calcium, that's bicarbonate, HCO3, or hydrogen carbonate. So the calcium bicarbonate to silicon dioxide to calcium silicate ratio is all going to be the same. So now the next thing is, for this, I look at the carbons, and there's 1 carbon here, and it's in the middle here. So that carbon, there's 2 carbons there because of the 2 there. So that the parentheses means that unit. So I know also by ratios, there's going to be a 2 here, a 2. I can even kind of lock this in. So I can lock in, there's going to be a 2-to-1 ratio between carbon dioxide and then one of calcium silicate, silicon dioxide, and calcium bicarbonate. So I can lock that in. And next thing I need to do is count up the oxygen atoms. I'm sorry, the hydrogen atoms. I guess I could count the oxygen atoms, but look at the hydrogen atoms. And there's two hydrogens here. Here's a different color. There are two hydrogens here, and then there are two hydrogens here. So actually we're on the same ratio then. The hydrogens are actually balanced. And now, then I have to look to the oxygens. So 2CO2, this is going to be 4 oxygens. And then we have 3 oxygens there from the silicate. And then we have 1 oxygen from the water. Now looking at the right side of the equation, we're going to have 2 oxygens here from the silicon dioxide and 3 times 2 or 6 oxygens from that. So sum these up over here, we have 8 oxygens and 4 plus 3 plus 1, this is 8 oxygens. So now looking at all of this, I have the carbons, the hydrogens, the calciums, the silicons, and the oxygens. They're all balanced. And so then I'm actually done. All I had to do is put a 2 in front of the CO2 to get that all balanced. But do you understand like my thinking process as I'm like thinking aloud, like, how do I solve this? Like, okay, I'm fixing ratios. I'm fixing that and that and that. So does that make anybody have any questions so far? Did you have a question, Andre?
I was saying you have to put the solution.
If you input it into mastering chemistry, yeah, I'll do it properly. Fine. It's going to be 2CO2 gas plus calcium silicate solid plus liquid water yields silicon dioxide solid plus calcium bicarbonate aqueous, like that. That's if you were to input that into mastering, you'd have to do it that way. So I do have the sloppy chemistry shorthand. So questions? So, okay, well, recap with this one. I looked for ratios, specifically with the atoms, and I want to lock in ratios. And the first ratio I found out was that for every unit of calcium silicate, since it has 1 atom of calcium, 1 atom of silicon, I locked in the ratio of actually both the products, because one of the products has silicon in it, the other one has calcium. And since the calcium and silicon is found only on one reactant on the left, and then that means that for every 1 unit of that reactant, we're going to have the same units of those products. So lock in that ratio. Then I look at the carbons and balancing out the carbons. There's 1 atom with carbon in it. I'm sorry, 1 molecule with carbon in it on the left. It's carbon dioxide. So, but on the right, calcium bicarbonate has 2 carbons in it. So I've got to double the amount of carbon dioxide to make that balanced. And then I look at the hydrogen balance, and the hydrogens are already balanced. And then I look at the oxygens, and then by doubling the carbon dioxide, I actually did balance the oxygens. So if I did not balance the oxygens, then I'd have to start looking at different ways to balance the atoms. So this is called an iterative process. You have to try something out, go back and fix, go try until you converge to an answer. So that's the way you do this. Questions so far? How about you guys in Zoomers? You guys doing all right?
Yeah.
Awesome. Okay, so for B, I'm going to show you another trick. So let me write it down so I have more room. Cobalt nitrate, it'll be cobalt 3 nitrate plus ammonium sulfide makes cobalt 3 sulfide plus ammonium nitrate. So you can balance, so something to note here and Zoom, I'm standing up and I'm pointing at something. Oh, I shouldn't stand up. I'm gonna block everything here. I'll move this up. So I'm pointing to the nitrate, the NO3. I notice that the nitrate on the left side of the equation, the nitrogen does not change at all. It stays hooked to the oxygen. So actually for the nitrate, I can lump that as one unit when I balance it. I don't have to break apart the nitrogens and then balance the nitrogens and balance the oxygens. I can just balance the nitrates because the nitrate is not reacting. Same thing with the NH4, the ammonium ion. This ammonium ion is not changing form. So if I were to go ahead, I mean, like, if I were to look ahead, I would think, okay, I've got 2 ammoniums and 3 nitrates, and the product only has 1. I'm going to kind of already think we have 2 and 3. We're probably going to have it by a multiple of 6. So because 2 and 3 are prime numbers, so 2 and 3 are prime numbers, and you have to multiply them together to find a common factor. So the factor is probably going to be, well, it's going to be a ratio of 6 somewhere. But I can just go ahead and, so since I've already identified that, I can go ahead and look at that going forward. So cobalt and nitrate. So I'm going to go ahead and, by the math logic, I'm going to put 2 and 3 here, and then that's going to be 6. Now I have to balance the rest of the atoms. And there's 2 cobalts on the left. And right now there's 2 cobalts on the right. The subscript there means that there's 2 cobalts. And, oops. And there's 3 sulfurs. So the 3 here, there's 3 sulfurs. And that's fine. So actually it's balanced. It's balanced already. So I guess how would you do this without that? I guess you could do it by counting up all the hydrogens and oxygens. That would be a lot more difficult. I guess we can go ahead and, well, I don't really want to do it that way because that would just probably confuse you guys. But there are some shortcuts to do this, and like one of them, like I said, since the nitrates are staying together and the ammoniums are staying together, you can just kind of lump them as one thing when you balance them, rather than having to go through. And that makes this problem a lot easier to do it that way. So again, the way to solve this one, I guess maybe I can do it. Let's do it another way. I don't know or is that a bad idea? I see another way to do it really easily. Is that gonna confuse you guys if I do it another way, or is it?
Start with the cobalt?
Yeah.
Okay.
Yeah, that's the thing. You have cobalt over here in one atom, and it's which one am I picking? Why am I picking certain ones? I pick the ones that are easy to find the ratios. So this cobalt here, there's 1 unit of cobalt, and I'm pointing zoomers. I'm pointing at the first one, the cobalt nitrate. There is 1 unit of cobalt in that, and then the cobalt sulfide, the cobalt 3 sulfide on the right, that has 2 cobalts. So I could go ahead and put a 2 here. And likewise with the sulfur, the ammonium sulfide on the left, there's 1 sulfur, and the cobalt sulfide on the right, there's 3 sulfurs. I can go ahead and put a 3 here. And then that's balanced. Now I have to, if you wanted to do well, I'll go ahead and do the atoms. You can do the nitrates like I mentioned before, doing the nitrates. There's 6 nitrates that are 2 times 3 is 6. But if I wanted to do oxygens, for whatever reason, if I was like, okay, well, let me do just plain old atoms. So let me balance it off with the oxygens. So then there would be 18 oxygens. So 2 nitrates is going to be 3 times 3 times 2. So that's 18. And then we have 18 on the left, and on the right, we have just we have here in the nitrates, we have 3. So 18 divided by 3 is 6. So you can do it that way. Then balance the hydrogens. Well, looking at the hydrogens, there's, so here we have 3 times 4 times 2, so we have 24 hydrogens there. 6 times 4 here is 24 hydrogens there. That's balanced. And then nitrogens, we have for the nitrogens, let me change colors. So 3 times 1 times 2, that's going to be 6. And 6 times 1 here is 6. So the nitrogens are all balanced. So you can do it atom by atom. So there are different ways of doing it. But as long as but the important thing, so right, science is a process. So everything is you can say anything is a science. Calligraphy is a science or something. What makes it a science? If it's a process. If it's a systematic process, it can be called a science. And so there is a science to balancing chemical equations. As long as you follow the system, you will get it correct. So questions with this one? Happy you guys are looking bored, or is it just, well, I'll just keep on going. What the heck? I got a lot of questions. Actually, the balancing equations is what I got the most questions from the students Well, you students. Okay, so next one. Copper 1 oxide plus carbon yields copper plus carbon monoxide. Okay, so again, looking at ratios. So we have 2 coppers. So over here, copper 1 oxide, we have 2 coppers. So we need 2 coppers on the right. And now looking at the oxygens, well, 1 oxygen there, 1 oxygen there, that balance is okay. Carbons, 1 carbon here, 1 carbon there, that balance is okay. And I guess we're done because we have 2 coppers, 1 oxygen, and 1 copper on carbon on the left, and 2 coppers, 1 carbon, 1 oxygen on the right. So we're actually just went ahead and balanced it that way. So remember system, follow the atoms and go forward. Questions with that one? This is a really easy one next. What do you mean by add? I put a 2 right there. Didn't hear the melodious sound of my voice? No, I'm teasing, of course. Well, supposedly college professors are supposed to have very soothing voices. So hopefully my voice is soothing for you guys. So other questions? Okay, next one. So hydrogen plus chlorine makes hydrogen chloride. So 2 hydrogens on the left with the H2. There's 1 hydrogen on the right with HCl. So you put a 2 in front of it. And now you look at the chlorines. You have 2 chlorines on the left. And now since you put a 2 in front of that, you include 2 chlorines on the right. And you're done. So that one's easy. So other questions? And just because I like to hammer things home, I'll do 4 more. So here is 424, part A, sodium sulfide plus copper nitrate, copper 2 nitrate makes sodium nitrate plus copper 2 sulfide. So let's look at the atoms. Start with the easy one, sulfur. So sulfur is one atom over here, one atom over there, only on one compound. So we can go ahead and balance that. We can set the ratios there as 1 to 1. Same thing with the copper. There's one copper here and there's one copper here. So I can just go ahead and lock in that ratio there. And now I want to balance the sodiums. And there is 2 sodiums right here, and there is 1 sodium right here. So what do? I put a 2 in front of that to balance the sodiums. And then I look at the nitrates, and there are 2 nitrates here and 2 nitrates there. So, and by balancing the nitrates, that's already balanced, and then that's done. And I'm doing, like I said, the trick where I'm balancing the groupings of atoms. That's only because the nitrate does not decompose or it turns into something else. So that only when I'm balancing the groups of things, if the atoms exchange, then you can't do that. But these atoms are not exchanging. So alternatively, I can balance the nitrogens. On the left here, there are 2 nitrogens. On the right here, there are 2 nitrogens. That's fine. On the left, there are 6 oxygens, and there are 6 oxygens there. So the oxygens are also balanced. So I can, if you don't like balancing the groupings, that's fine. You can do it atom by atom. So again, the grouping only works when it doesn't change. When the atoms don't exchange. So questions with that one? You guys are looking bored. Am I losing you? This one's a little harder, I guess. Dinitrogen tetrahydride. Is that hydrazine? Some of these have common names. Looks like a rocket fuel. Oh, wait, I shouldn't. I just written down the answer. Okay. So this one's going to be a little bit harder, but you still have to go with the system. So and I'm saying up and I'm pointing on the N2H3, there's 3 hydrogens over here on the left, and then there's 3 hydrogens on the right with the NH3, the ammonia. So that ratio between those molecules is going to have to be 1 to 1, because hydrogen is only found on the left on there's only 1 molecule on the left, and it's only found in 1 molecule on the right. So those have to be the same ratio. Now, if we carry through the nitrogens, there's 2 nitrogens on the left. And then if you have the 1 to 1 ratio between the N2H3 and the NH3, that means that if you have the whole nitrogen, the whole N2, you're going to have 3. So like what we have right now, we have 2 nitrogens, and now we have 3 nitrogens. And so one way you can look at this, you can balance it by putting a half there, and that would get rid of that. And then you multiply the whole thing by 2, or, kind of, if you've already guessed it, you multiply everything. Since these are 1 to 1 ratios, you multiply these by 2. And now when you look at this, when you multiply that by 2, you're going to have 4 nitrogens there, and you have 2 nitrogens there. So if you keep a 1 there in front of the N2, you're going to have 2 nitrogens, and then it's balanced. So, your question? Yes.
Yeah, it is H4.
Oh, did I do that wrong? Oh, shoot. All right. 2H4. Did I just write it down wrong? Okay, same logic though. All right, we have hydrogen on, did I really? Oh, I did it right on my paper. Crap. I just didn't copy it down. I'm sorry, guys. I'm really sorry. Although I did balance that one properly. So you have to look between, same idea. We have N2H4 and NH3. So the lowest common denominator, so it's hydrogen's only in those two molecules. So lowest common denominator between 4 and 3 is 12. So you have 12 on both sides. Now you count up the nitrogens. So 3 times 2 is 6. And then you have 4 here. So if you have 6 on the left and you have 4 there and then you have 2 there, then actually that's balanced. Yes, I did do that. I'm really sorry I put the 3 there. But hey, we got a bonus one then. Because I balanced it properly with the 3. It's the same logic. The same logic you carry through, right? You pick one and then you balance it and you go for the other atom type. Yeah. Thank you. And I'm glad that I'm recording this lecture so that everyone can remember the mistake I made. I see something in the chat box. Did someone have a chat? Very soothing. Okay, thank you. How do I get rid of this chat? Okay. I feel like Bob Ross. It's just a happy little accident. Okay. Other questions? All right. Next one, HCl NO2. Oops. All right, I'll make sure to write this down properly in this time. HCl plus O2 makes H2O plus Cl2. Is that right? Yes. All right, so balancing, I'm going to pick hydrogens. So there's 1 hydrogen in HCl and 2 hydrogens in water. So I'm going to fix a 2-to-1 ratio there between HCl and water. And now also for chlorines, there's 2 chlorines from the 2 HCl's and there's 2 chlorines in the Cl2. So now that ratio is set. Now I look at the waters. I'm sorry, the high oxygens, when I say what? Look at the oxygens, and there's 2 oxygens here and there's 1 oxygen there. So what do I have to do? I have to multiply everything by 2. And then that becomes 4. This one becomes 2, and that one becomes 2. And then now when I look at the oxygens, there's 2 oxygens on the left and 2 oxygens on the right. There's 4 hydrogens on the left, 4 hydrogens on the right, 4 chlorines on the left, 4 chlorines on the right, and I'm done. So, any other questions with that? I know I'm just kind of talking my way through the logic. And hopefully no one will have any other questions with balancing chemical equations. So we have iron 2 sulfide plus hydrochloric acid makes iron 2 chloride plus hydrogen sulfide. Smelly stuff. Smells like rotten eggs. Okay. So start with iron. There's 1 unit of iron on the left, 1 unit of iron on the right. So set that ratio. Then sulfur, there's 1 unit of sulfur on the left and 1 unit of sulfur on the right. So set that ratio. Now we have 1 unit of hydrogen on the left and 2 on the right. So I got to put a 2 there. And then chlorines, there's 2 chlorines on the left, 2 chlorines on the right. So that's all I needed to do was to put a 2 in front of the HCl, and then that balanced everything. So, questions of this? All right. All right, next one. Calculate the number of moles of nitrite from, that's NO2, when each quantity completely reacts. So this one actually not necessarily connected to the homework, but there's a few test questions that are just like this. So I wanted to make sure that you knew how to do this. So starting with 2.5 moles of dinitrogen pentaoxide. So do dimensional analysis, 2.5 moles N2O5 or dinitrogen pentoxide. And then next thing we want NO2. Oh, no, that's not, I'm sorry, not nitrite, it's nitrogen dioxide. I thought for some reason, I thought it was, sorry. It'll be nitrogen dioxide. And for there's 4 moles NO2 to 2 moles N2O5. And I'm getting that from that ratio. And this one, I don't need my calculator. You just multiply this through. This is going to be 5 moles NO2. So this one's a single step, and the single step is just the stoichiometric ratio. Stoichiometry is the chemical accounting. So in the balanced chemical equation, the ratios are called stoichiometric ratios. It's a stoichiometric ratio between nitrogen dioxide and dinitrogen pentoxide. So questions with the first part?
Just plug it in, right? The 2.5.
Yeah, 2.5 times 2 is 5.
Yeah.
5.0, you mean? You want the 2 sig figs?
Well, I thought it was multiple choice. An A, B, C, D, but it's just.
Oh yeah, this is free form. This is not multiple choice. This is multiple parts to solve the problem, or whatever, multiple things. Okay, so the next one's going to be a little bit more complicated. So I'll do it down here. So we're going to have 15.2 grams N2O5. And do the formula, the molecular weight of N2O5. So you're going to have, 2 times 14 for nitrogen plus 5 times 16 for oxygen. What is that? I should change the batteries in my awesome calculator. Okay. 28 plus 16 times 5. It's 108. 108 grams per mole. Okay. So then we have mole N2O5 to 108 grams N2O5. And then the next step is the same as the one on the top. It's just going to be 4 moles NO2 to 2 moles N2O5. And you could, I'm writing it down because it's what's on the chemical equation. I would just, when I put in my calculator, I'm just going to multiply by 2. I'm not going to multiply by 4 and divide by 2. I'm not going to do that. So, and I wants me to install another app. That's one thing about free apps. You got to look at the ads. Times 2 divided by 108. And do this way, so then this equals 0. How many sig figs? We have 2, 2, 8, moles NO2. So just wants moles NO2, right? How many moles? Yep. So 15.2. Yep, that's right. Okay. So that makes sense. Yeah, it does. Okay. All right, so second one, just a little bit, just another extra step there. But again, so for you as the user, you have to look at the given information. So we're given, instead of mass, so instead of moles, we're getting mass. So I'm trying to get you guys to think, okay, when I see mass, how many moles is that? Knee-jerk reaction, reflex, how many moles? Now we convert to moles of reactants. And now by the balanced chemical equation, we get the ratio, and then we get the moles of the product. And it's asking for the moles of the product. So, questions with this one so far? Okay. So, all right. Find the limiting reactant for each of the initial amounts of reactants. I thought A was too easy. It's a 2-to-1 ratio between sodium and bromine, and you're going to use sodium up twice as fast. So that means that sodium's a limiting reagent there. So I think that's probably obvious. And actually, I mean, looking ahead, then at B, it's going to be sodium again, because you're going to need 2.8 moles for the entire thing of to react all the way with bromine. But let's just go ahead and solve it like it wasn't obvious, so you can see the way to do it. So for B, then you have to go and figure out how much sodium bromide NABR product you're going to make. So if you start with 1.8 moles of sodium, and then you're going to have 2 moles sodium bromide per 2 moles sodium. And I'm getting that from that. And this is going to generate 1.8 moles of NABR. I know when I did the when I do it in like the example problems, I usually go all the way through grams, but you don't have to put grams for this one. It's just asking to just try and keep it simple. So you can turn it to grams if you want, but that just adds extra steps. And then looking at it for bromine, so 1.4 moles of bromine, and then it's going to be 2 moles sodium bromide per mole bromine. And let me do a different color. So of course, there's a 1-to-2 ratio, so make sure you have that for there, or it says say 2-to-1. So this is going to be then 2.8 moles NABR. So from this, looking at the ratios, if we're looking at this, you have to pick the lowest one. So the lowest one is the sodium. So the sodium is the limiting reactant. I usually say limiting reagent, but limiting reactant. Maybe I'm the one that's, I don't know.
I remember reagent.
Yeah. Maybe I'm just getting old. They switched it on me. Or yeah, I have to look in the textbook. It doesn't matter. It means the same thing. Reactant, reagent. Potato, potato, tomato, tomato. Right. So I guess they're different words and different pronunciations, so that may not be the best analogy. But does anybody have any questions with how this one works? Are you guys bored? You're like, I'm doing fine, but of course I'm doing math. I'm the one having fun here. I'm looking at your eyes through your mask. You're like, oh my God. All right, last one, then I can go into my reserve cache of problems. Okay. Magnesium oxide can be made by heating magnesium metal in the presence of oxygen. The balanced equation for the reaction is 2 magnesiums plus oxygen makes 2 magnesium oxides. When 10.1 grams of magnesium reacts with 10.5 grams of oxygen, 11.9 grams of magnesium oxide is collected. Determine the limiting reactant, theoretical yield, and percent yield. So a couple things. So magnesium from the periodic table is 24.31 and oxygen is 16. Again, those numbers I'm just getting from the bottom of the periodic table. So magnesium element number 12 and atomic weight of 24.31 grams. I went by when I wrote that down, I wrote by the periodic table that's in the textbook. So, okay, so how do we do this? So you figure out the limiting reactant, reagent, however you want to say it. So you have to do both of these. And I'll look at my notes. Yeah, I went down to grams. Yep. So we have 10.1 grams of magnesium. So I want to go from grams of magnesium to grams of magnesium oxide. So how do I get from grams of magnesium to grams of magnesium oxide? I'm going to convert to moles of magnesium. Then I'm going to look at the ratio between the balanced chemical equation. And then I'm going to go back to moles from moles to mass for magnesium oxide. So let's go to moles magnesium. So moles magnesium to 24.31 grams of magnesium. And then now we got to convert to moles of magnesium oxide. So 2 moles magnesium oxide to 2 moles magnesium. Again, I'm just writing that down. I wouldn't even, when I calculate that, I'm just going to skip that step because 2 divided by 2 is 1. And I might even just write 1 mole magnesium oxide per mole of magnesium, but I'm trying to emphasize that it's balanced there. And then you look at magnesium oxide. So 24 plus 16, that's 40, right? 40.31. So then that would be 40.31 grams magnesium oxide per mole magnesium oxide. So, and if you're wondering where the magnesium oxide is, so you just add these together, right? 4 plus 6 is 10, and 10 plus 20 is 30, plus 10 is 40, so then 40.31, so to be 40.31 grams magnesium oxide per mole. Okay, but then if I do this and I calculate it out, I get 16.8 grams of magnesium oxide. And then let me do it for oxygen. 10.5 grams oxygen. So mole O2 to 32 grams O2. And then we have 2 moles magnesium oxide per mole O2. Notice again, though, that this ratio, actually there's different colors. So the 2 here and the 1 there, right? So make sure you keep that proper ratio. And then same thing, 40.31 grams magnesium oxide to moles magnesium oxide. Doing this, you get 26.5 grams magnesium oxide. Now, if you follow the examples in the book, they stop at moles and then mark what the limiting reagent is. I just like to go ahead to grams because I don't like to stop and then start again. I just like to chug all the way through, but that's my own personal preference. It's if you want to stop at moles and then restart again, that is totally valid. You can go ahead and do that. But obviously this one here is the limiting reactant, and well, it means that the magnesium is the limiting reactant. It's also the theoretical yield. Our theoretical yield is 16.8 grams. And the percent yield we get, so the percent yield then, the percent yield is the actual over the theoretical times 100%. So your actual is 11.9 over 16.8 times 100%. And if you do that, you get 70.8% yield. Which actually 70% yield for a chemical reaction is decent. It's a bit low for magnesium because if you ever done this, it's fun. You burn magnesium. It's really, really bright. Actually kind of burns your eyes. Actually, you start seeing flashes. You start seeing at least for my vision, I see the whatever the red dots whenever you in your vision, like when you stare at the sun. Okay, but recap for this one. We have 10.1 grams of magnesium, 10.5 grams of oxygen, yields 11.9 grams of magnesium oxide. We're going to figure out what the limiting reactant is, what the theoretical yield is, and also the percent yield. So what do? We start off with both reactants, and we figure out how much product we can get from them. So the way we figure out the product is we convert from mass of reactant to moles of reactant. Then we convert to moles of products using the balanced chemical equation, and then back to mass using the molecular weight of the product. And we find out that the limiting reactant is magnesium, and we have a theoretical yield. We should get 16.8 grams of magnesium oxide. That's assuming everything reacts and goes all the way forward. But we were given that we only get 11.9 and we should get 16.8. So that implies we have a 70.8% yield. Then for the percent yield from this chemical reaction. So questions with this one? Nope. Okay. So obviously I'm done with the notes.
Wouldn't it be 16.7?
Did I calculate it wrong?
For the top part.
Wait, this one right here should be 16.7?
I don't know, it makes percent like a big difference at the end.
All right, let me recalculate. So 10.1 divided by 24.31 times 40.31. Yeah, I see 16. How did I get 16.8 then?
When you round the thousands plates to the hundreds, it becomes a 5, and then that rounds it up to
Okay.
the tens.
So 16.7 and then 11.9 divided by 16.7. So 71.3. 71.3. I guess I had a rounding error, but the process was good though, I think. But, oh, question?
It's not about this one. It was just a specific question on one of the homeworks I was wondering if you'd be able to do if we have some time.
Yeah, which one?
It's calculate the empirical formula for 0.294 grams lithium and 5.381 grams iodine.
Okay,
And this one is just a little bit different than the one you did in the beginning because I believe it comes out with like not round numbers.
yeah, okay, can you give me the numbers again?
Oh, yeah, sorry. 0.294 grams lithium and 5.38 grams iodine.
5.3 what?
5.381 grams iodine.
Okay. So making me go off script, are you? Okay, we gotta. Okay, so we have to look to our handy dandy periodic table. And if you look there at lithium, it's 6.94. And iodine, it's right there, 126.9. How do you cancel? Okay. There's cancel. Okay. So then mole lithium to 6.94 grams lithium. And I'll just do the lithium first. So who's got the calculator? We'll do this class. Who's got a calculator handy? Oh, you can go ahead.
Oh, what's that?
Yeah, what's 0.294 divided by 6.94?
0.042.
When 0.042. You said?
How many decimal points do you want?
3.
0.042.
One more. Yeah. That's 3 sig figs. Okay. Then mole iodine to 126.9 grams iodine.
0.0424.
0.0424?
I think I got mixed up on this one.
Because then that should just be 1-to-1.
Sorry, this sounds stupid. I printed out the periodic table and it's kind of fuzzy, so I thought iodine was 176.9 grams, and that's what's screwed me up.
Okay,
Sorry about that.
no worries. But that also makes sense because lithium tends to be +1 and iodine tends to be -1. Question?
It's not like a specific question like this, but like when we're taking the test and say we have to sort the periodic table stuff, you know, some formats they don't allow us to like switch tabs. Like you can see on
I don't have security on it.
it doesn't. Okay.
Yeah, there's no
Sorry, 'cause
security.
I have classes where you can't like switch tabs or allow periodic test.
Yeah, I don't have the, I know that mastering doesn't have that capability. You can do it with McGraw-Hill, whatever I forget the name of the software. But yeah, no, I don't have that security to this. So you can feel free to, I mean, it's really hard to Google chemistry though. I mean, you can Google parts of it, but you're not going to be able to Google all your answers. So, okay, so if there's any other thing you guys want, if not, I'll go to my other prepared stuff. Actually, did I have one on chapter? Yeah, I know. I forgot my my charger. How am I for battery? Oh, it's 12%. Hopefully it'll last. Okay, I know I had, I'm kind of focusing on chapter 4. Did I have, let me see what I have there, chapter 4. Oh, I already did this problem. I already did that, okay. I did a problem like that. And I've already done about balanced chemical equations. Yeah, it's gonna be a lot of math. I was looking at your homework and where people had trouble with. Okay, here's a good one. It's a fast one. So it's going to be, which answer is this? 3.69. So, so sugar crystal, sucrose crystal still has 1.8 times 10 to the 17 sucrose molecules. What is the mass of sucrose, which is C12H22O11 in milligrams? Okay, so to figure this out, so this time we're given molecules and also 2 sig figs. So you have 1.8 times 10 to the 17 sucrose molecules times mole of sucrose over 6.02 times 10 to the 23rd. I'm gonna write that out. There we go. So then that gives us moles of sucrose. And so we need to get rid of to go to grams. So moles of sucrose is on the bottom, and then you get the molecular weight. So it's going to be 180 times 2 minus 18. Oh, gosh. My battery is going to be going soon. What is that? 180 times 2 divided.
64.
No, it's going to be 2. 2 is going to be the last digit. 180 times 2 minus 18, 342. 342 grams sucrose. And where am I getting that from? So looking at this, it's going to be 12 times 12 plus 22 times 1 for hydrogen plus 11 times 16. But I know that glucose is 180 and there's 2 of those and it's got a water pops off. So it's 2 times 180 minus 18. So 342. And the last step is then going to be 1,000 milligrams sucrose to a gram of sucrose. And then that's dimensional analysis there. Geez, and my battery is dying, isn't it? How much battery? 9%. Okay, I can make another 10 minutes, I hope. So, do you want to know the answer? You must know the answer at 0.10 milligrams sucrose. Looking at the answer. So, but the way you do this is dimensional analysis. I noticed that the molecules cancel, actually, units molecules cancel, the moles sucrose cancel, the gram sucrose cancels, and you get milligrams sucrose. So when you have the proper terms divide and they cross cancel, the units cancel, and you get the proper answer. So. Any questions with this one? Out of curiosity, I know a lot of people got this wrong. Why did you, just what your thinking was, what did you get stuck on? Because we started with molecules instead of mass or something? You didn't know how to go from molecules to moles? Are you just, okay. That's what
I would be confused if I did this one, molecules and moles.
yeah. I mean, that's one thing about chemistry that like, you can't, there's not one way to solve all the answers. You have to, you have to logic your way through all the problems. So you can't, like I said, we don't have computers that can do this. It's a human thing right now. Okay. And I know I didn't really cover this one in class as much. So I guess I can kind of see why people didn't get this one right. 3.36. So what's the compound that forms between sodium and carbonate? So sodium and carbonate. So sodium is an alkali. It's going to form a +1 charge. Carbonate, you look up, and it's -2. So when you make a compound between these two, you have to balance the charges. So if you have a +1 charge for the metal ion, and then the -2 for the carbonate, you're going to need 2 sodiums. Oops, that's nitrogen. You're going to need 2 sodiums, carbonate like this, because the sodium is +1 and the carbonate is -2. And I know, I guess the mastering does this. So you have to have the 2 positive ions counteract the -2. And the way that you balance these is you always look for the lowest common denominator. So the lowest common factor between them. And in the case of 1 and 2 is 2. So you have the 2 there. Question?
I got stuck on trying to figure out why carbonate or like phosphate was a negative charge, or like how much it was a negative charge, or like how many oxygens were in the 8, the carbonate or the
Yeah.
phosphate?
At this point in time, you would just look it up
Okay.
for that. And I don't think there's a problem like this in the test. I'm not sure. I have to double check, but I wanted to make sure that you knew the logic behind it. So right now the logic, and we will talk about carbon, the polyatomic ions and the charges. We'll learn about that near the end of the semester. And
Nothing to do with orbitals, right?
well, the answer yes, but I mean we talk about it with Lewis theory, so
Right.
orbitals would be a more advanced topic. So, and the next one is sodium phosphate. So sodium and then phosphate. And sodium is Na+, phosphate is PO4 -3. Oops. So same logic. So same logic, you have to have 3 of the positive charges to counteract the -3 charge. And what's the next one? Oh, and the sodium biphosphate. And then we have the next one saying sodium and then hydrogen phosphate. And I said the word bi. In chemistry, bi means an extra hydrogen. So carbonate, bicarbonate is carbonate's H or is CO3, bicarbonate is HCO3. phosphate is PO4, biphosphate is HPO4. So it's going to be Na plus and then HPO4 minus 2. So and that H there brings up to -2. And you just look it up at this point in time as far as the ions, the ion charge, and then you have Na2HPO4 like that. Is there another one? Ooh, there's a lot of them. Sodium acetate. Okay, next one is potassium and carbonate. Potassium is an alkali, +1 charge, carbonate already covered, -2. Sorry, 2 minus. So same idea, you need 2 of the positive charges to counteract the -2. The 2 positive potassium ions counteracts the -2 carbonates. And the last one, or as I said, look at the audience. You guys, are you following that logic? Last one, it's sodium and acetate. Let's see here. Acetate, it's this molecule. So it's C2H3O2. Okay, is that what it has in the book? Yeah. C2H3O2. And this is going to be an acetate is actually a negative charge, and so +1 -1 is just going to be then sodium C2H3O, just like that. And I'm looking at the answer. There's a couple of acetate. Sometimes you can see this written like that, but I didn't teach you that, right? And the book didn't really show. Oh, gives a couple of ways to do it. I'll stick with what's the way that it goes that way. Anyways, let's talk about some other things. So let's say that you have iron +3 and an oxide. You have to figure out what the balance is for this one. So when you have 3 and 2, your lowest common denominator is 6. So this is going to be Fe2O3. And what's another one? So maybe we'll do tungsten and nitride. Tungsten can be +4, nitride is -3. So I don't even know if this molecule exists, to be honest with you, but I just want to show for how you balance them. So the lowest common denominator between 4 and 3 is 12. So that would be W3N4. What's one? Say you have lead +4 and O -2, so lead 4 oxide. Lowest common denominator between 4 and 2 is 4. So you would have PbO2. So don't automatically think, oh, so don't just think, okay, I'm gonna have Pb2O4. I guess you could do it that way and then look for the lowest ratio, but I tend to do my thinking up front. But are you guys following the logic there, how to balance the charges? Okay. Yeah, lowest common denominator. And I got 2. Anybody have any last minute question? Well, literally a last minute question because there's a minute left in class. No last minute question. What about you, Zoomers? Are you guys doing good? All right, I'm assuming you're doing fine. I hope in that case, I'm gonna go ahead and end the class. I'm gonna jump on my office hours on my other computer because my battery's about to die on my computer. So does anybody want to talk to me in Zoom land? Nope. Okay.